Good morning. Um, I did not get my lecture recorded last night, and so therefore I'm recording it this morning. I did not have a good day yesterday. These things will happen under the pressure of a crisis like this. I'm going to be quite frank about things because I think it's better if you understand you're not in this sort of stuff alone. I spent much of my day sort of disengaged. It was hard for me to get work done. It was hard for me to concentrate. As it was, I managed to do some advising, managed to hold a couple of student meetings, managed to help some people with their program 6, managed to have a hour-and-a-half meeting on using Zoom, which obviously I've been doing. Exchange some text messages and email about layoffs that occurred at the university yesterday. My understanding is we had about 40 staff people laid off. It was a rough day. It was just a rough day. And yet my day was quite full. It was quite packed. I'm hoping today is better. And so I'm starting today with you, and we're going to roll back a little bit of what we did yesterday. And this is something that, again, I'm going to be quite frank about. I am struggling right now with an accessor. So the mutators are fine, but the accessors, the getters, for strings and arrays are kind of vexing me. I've been programming in this language for 33 years, and I'm having struggles with return values out of functions. Oh my God, return values out of functions, you should have that down after 30 some years. Not necessarily. So this is some quirky stuff. I'll figure it out. I've already figured out the getter for items in the cart. It essentially is get a specific item one at a time. Do not try to return the whole array. For the strings, I'm still mucking with the last name string, the getter for last name. And so when I get that figured out, what I'll do actually is just post some of the test code to Moodle, okay? That doesn't mean that you have to not start. That doesn't mean that you shouldn't start on your program 7. Start on program 7. You must start early. The amount of panic emails that I received, Monday and Tuesday, I literally, well, I guess I could go look. Let me go into my email real quick and look at how many of those I received. 1, 2, just in the last 2 days. And as you can tell by the amount of time it takes me scrolling, so this is just Monday and Tuesday. 3. Okay, and then into the folder, because I've already archived a bunch of these. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 emails on the day that the program was due or the day that the program was originally due before I extended the deadline. Each of those 20 emails requires me to read code, to look at it, to try to debug it. So I have said this before, I will say it again. Do not leave these until the last second. It hurts you. It hurts your ability to get your questions answered. It hurts your ability to get a good grade on the programs, to get the programs finished. Too much waiting until the end, too much ignoring the things that I had shown you in lecture, too much going off, and I'm not sure if you're asking other people for help, if you're looking online for help, but I saw a lot of weird code that was not anything like what I had shown you in class. Most of that program I gave here in lectures. Why would you go somewhere else and pull in code from who knows where? That is a typical response to panic. Oh my God, it's 11 o'clock at night, it's due at midnight, and the professor isn't going to be online right now, and I'll Google it. No, start early, start early. Start 7 now. Start laying out the queue. Because the queue doesn't require app data, well, it needs an app data, but your app data could just be the characters from the last program. Or not the last program, from the example that I gave for the last program, changing it to use app data. Just do that. Start on the queue. Start implementing the queue. Start doing push and pop. Okay, is empty, all of that stuff. All of that was in a lecture. All of that was in a lecture just a couple of lectures ago. So there. Start. Don't delay. Now, I'm going to mute video. And what I'm going to do today is lecture on the last topic that we will have for this term. Now you're going, well, wait, we're 3 weeks from the end of the term, right? 3.5 weeks from the end of the term. Why is there only one topic left? Well, I might have time for a second topic, but this topic, this particular topic, is going to take you some time, okay? It is going to eat you up a bit, okay? So pay attention. We've used stacks and queues so far, and stacks and queues are basically a specialization that is a more limited version of a generic list. So a stack is a list where you add to the front and you delete from the front. A queue is a list, but you're restricted to adding at the end and deleting from the front. A list is has no restrictions on addition or deletion. That is, you can insert anywhere in the list and you can delete anywhere in the list. So there are lots of collections of data that come in lists, grocery lists. If you don't believe that grocery lists are ordered, then you don't shop very much. I order my grocery lists when I do make them, and that's not that often, by the layout of the store. I'm going to get my fruits and vegetables first, because as you walk through the doors, the fruits and vegetables are there right on the left. Okay? And then any bread or bagels or English muffins, Okay, you're moving your way back through the store. Next, baking supplies, flour, that kind of stuff. Gluten-free is close to that area. Then we get into the frozen, then we get into more frozen, then we get into dairy. I order my grocery list that way. Employee lists. We could have a list of employees ordered by a couple of different things. It could be by last name and then first name and then middle initial. It could be by employee number. It could be by salary. It could be by date of hire. Okay. But there are orderings to that list. Telephone directories. This is sort of an old-fashioned concept, the telephone book, but they're ordered mainly by name. Class lists. I keep your class lists ordered by name, except I will reorder them by student ID number when I'm done grading a test. And that makes it easier for me to look up the student ID number on the test and find out whose test it is. So I would argue, some of these have a key value that orders them. Some do not. So a grocery list doesn't have a key. And by a key, I'm talking about an idea that we use. We also use this in databases. The key is a unique identifier for items in the list. So grocery lists, the items in a grocery list don't have a unique identifier. And so there's this course ordering potentially of location in the store, but that's not an actual key. Employee lists definitely do, telephone directories definitely do, class lists definitely do, okay? So they have key values. Arrays would seem like a natural way to implement a list. You have an array of structs or an array of classes. That is, it holds multiple pieces of data of the same type. It allows access to that data anywhere in the list. It allows you to manipulate the parts or the whole of the list as the array. But it causes problems because when you have a key value and you want to keep the list ordered, you're going to be shuffling things around in the list. If you want to insert in the middle in an array, you have to shuffle things to make room for that insertion to occur. When you delete something out of the array or remove something from the array, then you have to shuffle things in the array to bring everything close together, to eliminate the space that was once occupied by the data that's no longer there. So that causes problems. And arrays have a fixed size. I could guess at an array of employees. Oh, this company will never have more than 100 employees. Oh, this company will never have more than 1,000 employees. I worked for a company that had worldwide 130,000, 140,000 employees. That's hard to do in an array, simply because you have to guess at how many there are going to be. So now here's a little bit more discussion on that array problem. If we want to add a new person to the telephone directory array list, then we have to make room for it. So you have all this shuffling of data. Sometimes you don't have to shuffle at all. If you are inserting somebody whose last name is Zizaji, well, then that goes at the end of the array or the end of the list because they're the last person alphabetically. If you have to insert somebody whose last name is Aardvark, you have to shuffle the whole array. All of the data has to move down by one in the array to keep it in order. And this is actually an algorithm for sorting called insertion sort. It's not very efficient. And I never use insertion sort in arrays. There are better options. So no matter what it contains, And whether it is a class or not, a list needs to have the following operations. You have to be able to create a list. You have to be able to destroy a list. So that's our constructor and our destructor. You have to tell if the list is empty. You really should have something that tells you how many pieces of data are in the list. You're going to have an insert routine or an insert method that puts new data into the list. You're going to need a remove that removes data from the list. You're going to need probably some sort of retrieve, which returns either a reference or a value of a specific piece of the data. And we're going to need to be able to print all of that. So dump all the data to a stream. Okay. So that's sort of the bare minimum. You know, if you think about this in object-oriented terms in a class, constructor, destructor, that's a query on whether it's empty. Get length is probably a getter. We would store the length as a private data member, an integer in the private data. Insert is a mutator. Remove is a mutator. Retrieve is a getter. And print is just an overloaded stream insertion operator. Okay. So if I were to lay this all out in a class, I've got a class list. In public, we have the constructor, the destructor, the isEmpty, the getLength, the insert, and I've got insert now returning an integer, which is basically did an error occur. That's the only reason that we have a return value on insert. For now, I'm going to say insert at this index, one of these items. And so instead of calling these things app data now, I've changed it a little bit. Before we were calling them app data, now it's list item type, okay? Remove int position. So I'm setting this up to work just like an array. So you've got indexes, where you want to insert, where you want to remove. A retrieve, which returns a list item type, that is application data, and a display. In my private, I have the size, and then I've got the array, okay? An array of list item types. So this is an array implementation of a list, and we're going to see some of the ugliness that occurs here. The constructor simply sets the size to 0. That's it. The destructor sets the size to 0. There's no dynamically allocated memory, so we don't have to worry about it. IsEmpty returns if my size is equal to 0. So if my size equals 0 returns a true, then IsEmpty returns a true. If it's a false, then it returns a false. GetLength returns my size. Insert, oh my goodness. This is why using an array is ugly and time consuming. So we're going to insert at index the thing item. So we need a local variable int I. And then if the index that we're trying to insert at is less than 0 or greater than my size. Now think about the way my size works. You have to be careful of a one-off error in this case. My size, say 12, is 12 things in the list. Those will occupy indices in the array 0 through 11. So if the index that you're asking to insert at is greater than this, in my example, 12, it's out of range. You can only insert at, or if it's greater than 12, you can only insert at 0 through 12. So we produce an error and we return 1. Else if my size equals max size. So if we have exceeded the maximum size of the array, if the array is full, you can't insert either. And so we output an error, the list is full, and we return 2. Otherwise, we have to shuffle space. So for I equals my size, I greater than index, I minus minus, my array I equals my array I minus 1. So this is shuffling data from the end. And then my array at index equals item, my size plus plus, return 0. That is not an easy loop to set up. It has a lot of potential for off by ones and boundary condition errors. We've taken care of the boundary condition errors up here. You know, we take care of the off by ones by carefully testing this loop, but that's ugly. This is just some ugly code, you know. Remove. Similarly, you got to check to make sure that you're removing something that's legit. This time, you're removing something, you know, if your index is less than 0 or greater than or equal to my size, you can't remove because the index is out of range. And then you have to shuffle, but this time you're shuffling from where you're removing to the end. And so the loop runs the other direction. This loop was running backwards, you know, starting at the end of the array and bouncing backwards. This loop is starting where you're removing and it's bouncing forwards, shuffling everything back by 1 spot. So I equals I plus 1 here. So this is moving the data slowly backwards. And then my size minus minus. Here's a retrieve. That one's not too bad. You bounce check it and then you return it. Okay. And display, just print it out. Again, not too bad. Now, list item type was not defined. We really shouldn't worry about that because the user of our data structure, the downstream developer, is the one that's going to supply us with list item type. Now, in order to do this, the downstream programmer is going to have to do things like overload the relational operators. We haven't done that yet. We haven't seen that yet, but that's what's going to happen. They're going to have to overload the relational operators. So one of the ways to determine this is looking at the code where we used list item type, okay? So we passed it as a parameter to a function, okay? So we need a copy constructor. We return it as the return value from a function. So that again is the copy constructor. So passing an argument or returning a value requires something we call the copy constructor. List item type my array max size, that's not really a problem. Here, we're shuffling things back or shuffling things forward, you know, so there's an equals, there's an equals, there's an equals. So we need the assignment operator overloaded for list item type. Return, we need the copy constructor again. Cout, we need the stream insertion operator overloaded for list item type, okay. I think I missed one. Let me check. Nope, I didn't. Okay. So here's a list item type that's going to have everything that we need in it. That is public with a constructor, a destructor, a copy constructor, and an assignment operator overload, and a stream insertion operation, operator overload. Some private data, ID, and salary. That's all it is. It's an employee list. Okay. So that was all for the implementation of an array-based list. You do not want to do array-based lists. They're ugly. They take a lot of time. Okay. And you're limited in how many slots of data you have or how much space for data you have. So linked data structures, you know, can either be dynamically or statically allocated. A natural implementation is dynamically allocated using pointers, just like we did with the stacks, just like we did with the queues. Sometimes we use static allocation, but not always. Static allocation is almost always reserved for small microcontrollers that have very little memory on board. So linked data structures all follow the same form. Node that has data relevant to the application, and also the node that links to other records or other nodes. So the simplest linked data representation is a singly linked list. There is an animal out there called a doubly linked list. And a doubly linked list, once you learn how to use them, you will never use a singly linked list again. It's just the way it is. So each node contains application data and a link to the next record, just like the stack, just like the queue. A variable contains a link to the head of the list. We called this front for both. Well, we called it head for the stack, and we called it front for the queue. Okay. Now the last node in the list either links to the head, which forms a ring, or it has a null link, so it doesn't point anywhere. Rings have a lot of extra code that have to be written to use them correctly. And so we aren't going to do rings in this class. You should just know that those things exist. One of the places that you would use those is in computer graphics, representing polygons. So a list of vertices where the last vertex in the polygon is, connected to the first vertex. Null is defined in most languages and is a value that can't possibly be a link, such as 0 or -1. And as we've seen, lists can be used to implement other data structures. In fact, we've already seen stacks, queues. So here's a linked list. The head pointer points to the first item. So the head pointer contains the memory address of the first item in the list. The first item has application data in it and has a link to the next item in the list. This continues on until you hit the end of the list that has a link of null, and that's it, okay? So for insertion, we have a normal case insertion that inserts a node in the middle of the list, and it is ordered by key values. So initialize a pointer to the head of the list. We're going to walk this pointer down looking for the first node whose value is greater than the data we are inserting. And this basically assumes that the ordering is from least to greatest. So if I'm trying to insert 12 and I look at the head of the list and it's 3, I know I have to insert after 3. I just have to. 3 is less than 12. So you want to keep walking the list until you see something that is greater than the thing you want to insert. So I move to the second thing in the list and its value is 7. Nope, 12 is still bigger than it, okay? Then I move to the next thing in the list and its value is 11. Nope, 12 is still bigger than it. Move to the next thing in the list and it's 22. Hey, that's bigger than 12. That's where I need to insert. Once found, we use a pointer that was shadowing the original one, that is one step behind, and we use both of those pointers to insert the new data. So here's a depiction of this, okay? We have 3 cities in our list. They are Atlanta, Dallas, and Syracuse, and we're about to insert Detroit. At this point, you can't tell which data value is the key. What determines less than or greater than? Because Atlanta is alphabetically before Dallas, which is alphabetically before Syracuse. You also have 203, which is numerically before 475, which is numerically before 578. And now you got Detroit. And Detroit is either going to go off the end of the list or in between Dallas and Syracuse. So let's do the insertion. We have a test pointer and a previous pointer. The previous pointer is null. The test pointer is pointing at the same place head is pointing. We check to see if Atlanta is greater than Detroit, and it is not. So we set the previous, we copy tests data into previous. So test's memory address goes into previous. And then we set test equal to test arrow next, moving it down. Okay. Head, we don't touch. We just get its initial value into test, and that's it. Okay. So then we check Dallas. Is Dallas greater than Detroit? No, it is not. So we're going to move test's address. The test is a pointer. Its address is going to get copied into previous. So previous now points the same place. And then test is equal to test arrow next, which moves it down. And then we check test arrow data again. So list item type or app data. And we ask, is Syracuse greater than Detroit? Well, it is if this is alphabetical, and it is not if this is numerical. So it turns out that we are indeed keeping these things alphabetical. So we allocate new space into previous arrow next. So let's go back and look at that. Right now, previous arrow next, that's Dallas's next, is pointing at Syracuse. We need to insert Detroit in between Dallas and Syracuse, which means Dallas needs to point at Detroit and Detroit needs to point at Syracuse. So we allocate new space, dynamic allocation of memory, okay? We're going to move previous. So previous was pointing at Dallas, but we actually, our business with Dallas is done. We altered its next pointer, and that's all we needed to do. So we're going to move previous to previous arrow next. That moves us here, okay? And then we're going to copy over the data. So we copied over the values, 672, and then we string copy Detroit into previous, okay, into the node pointed to by previous. Then we need to set previous arrow next equal to test. Test indeed is still pointing at Syracuse. It's just waiting to do its thing. And so we copy that value out of test and we put it in previous arrow next, and that links us up. And we're done. We have inserted a new node. Now, for those of you who are wondering, the numerical values are the altitude above sea level. So Atlanta is 203 feet above sea level. Dallas is 475 feet above sea level. Syracuse is 578 feet above sea level. And Detroit is 672 feet above sea level. There you go. So implementing linked lists using pointers, the list of objects have application data and a next link that is a pointer to the object for the next record. The compiler and runtime environment of the program handle the free space, and so new is used to require new space, just like in the stack and queue. The programmer handles list insertion, deletion, and searching an output. A data member called head is now a pointer to a class node, okay? And so when you need to add a node to the list, you need to new some space, and then you need to link the new space into your list in the proper spot. When you need to remove a node from your list, you need to find the node, if it exists, unlink it from the list, and then use delete to return the node to available space, so to the free space. And this step is crucial since C++ does not have garbage collection, okay? Now to keep it ordered, in almost every linked list, the data will have a value or values that are used as a key in order to keep the data in the list in order. So we were using the key city name, and Detroit was in between Dallas and Syracuse alphabetically. So simply put, Given two pieces of application data, oh my goodness, PowerPoint autocorrect, two pieces of application data, given two pieces of application data, you should be able to answer questions like, is data one less than data two? Is data one greater than data two? Is data one equal to data two? You need those relational operators defined, okay? So we're gonna do some operator overloads. I dislike overloading, I really do. And the reason I dislike overloading is that there's a lot of really, particular pieces of the syntax of the language that you have to use. So you've already seen this with the stream insertion operator overload, the assignment operator overloads that we've done in lecture before. Those things, some of them have friend on them, some of them don't, some of them need to chain an item type back, some of them need to chain the stream back. And so they're ugly. They're actually really ugly to write the code for this. Now, the relational operator overloads, here's a trick. And this trick saves you so much headache and time in testing. You only write the code for one of the operator overloads. I chose less than. Okay, so you write the code for less than, and then you define all of your other operators in terms of less than. So if I want A less than B, okay, I write the code for that. If I want A greater than B, that's the same as B less than A. So I use the less than to create this. A is equal to B. Well, that's not A less than B and not B less than A. So I can redefine equal to using Boolean algebra as this much more complex Boolean algebraic statement or Boolean expression, but it only uses the less than. A less than or equal to B is not B less than A. Again, these are identities, and I guess they're just identities. These are identities in Boolean logic. And so, again, I've redefined less than or equal to as by rearranging the items here and making it a not less than. A greater than or equal to B is defined as not A less than B. And A not equal to B is defined as A less than B or B less than A. So notice that I've only used the less than that I wrote the code for originally. I use not, which is a Boolean operator, or, which is a Boolean operator, or a logical operator, I should say. So these are, not is a logical operator, or is a logical operator, and is a logical operator. And so those don't have to be overloaded. Just this one, and then everything has to be written as I've laid out the Boolean algebra identities. Now, what are the weaknesses of a linked list? Well, I have to use 2 pointers to insert. I can get away with just one, but it makes the code much harder to write. There's several special cases. If you insert before the head, then head has to move. If you insert after the tail, then your trail pointers, your test is going to walk off the end. And if you insert into an empty list, you've got to handle the empty list case. It uses both a statically allocated node to hold the data while we're searching for it, and then dynamically allocates a node when we finally insert. And then we need to copy the data over, so we need a assignment operator overload, probably. Okay, so what's the algorithm? The algorithm and the code are going to be not hard to come up with, but let me stop the sharing here. I'm going to try something and we'll see if it works. So here's the algorithm. Okay, so let's do insert. Oh my God, this is horrible. I need like a Wacom tablet and a pen or a touch screen, and I do not have it, so I'm trying to write with a mouse. Oh, this is horrible. Okay, so to insert. So the first thing we have to ask is the list empty? Okay, and if it is, I'm just going to mark that as special case. So we have to have code that does that. Next thing we need to do, now that we have a list, so this is in the else. Okay, so now that we have a list, eraser. Let me clean that up. This is like the worst thing ever. Why did I even decide to do this? Stamp, draw. Okay. So in the else now, so if the list exists, we want to find the insertion spot. Okay. Once we find, and this is going to be a while loop. So the while loop is that's a programming idea. It's not part of the algorithm. The algorithm is just a list of steps. Okay. So find the insertion spot. We're going to do that with while. Let me do this way. So is it before the head? That's a special case. Is it after the tail? Or the end of the list? We don't have a tail pointer. So is it after the tail? That's a special case. Okay. If we get to this point, it's a normal case insertion. Okay. So that's our algorithm. If we want to insert an item, we have to ask if the list is empty because you can't search an empty list. If it is empty, that's a special case. Otherwise, we use a while loop. You know, we find the insertion spot. Then you have to ask, is it before the head, is it after the tail, or is it normal case? And so the way that we do that, that sequence might change a little bit depending on the code and how we write it. So that's our algorithm. That's exactly our algorithm. Now, I'm going to write some code. Now, the code that I'm going to write, over here. Lecture 11. Okay. So that's our linked list PowerPoint slides. And I'm just going to call this pseudolist.cpp. It's pseudocode. Most of it's going to look like regular code, but we have a lot of variables that we haven't defined yet, etc. So what I'm doing is I'm writing code, essentially planning that this is going to be inside of a class. And that class is going to have a list node struct in it. And we're going to have a list item type. Oh, I need a name on that. So I'm just going to call it data. Okay. And then prior needs to be null. Okay. You need to check to see if the list is empty. Now we could use is empty. And that's probably, that's the object-oriented way of doing this. So there's, if it is empty, okay, we need to allocate space into head, because head is empty, right? Head is null. So head is equal to new list node, okay? Head arrow, whatever we call this. I'm going to call it app data. Yeah. Okay. Whoops. I'm going to change this a little bit. I don't like the name. I'm going to call it data to insert. You pick better variable names and the code essentially documents itself. So I guess app data is good enough there, but I'm thinking node data. Now node data is going to be of list item type, okay? And then the last thing we need to do is make sure that the next pointer is equal to null. Look at that. That is the insertion for the special case of inserting before the head. Or no, excuse me, empty list. Okay. Down here, I'm going to have an else. Okay. And then in the else, remember we needed to find the place to insert. Now this is that whole, we were inserting Detroit. And so what we need to do, test is equal to head, prior is equal to null, okay? So we're gonna start a while loop, and we're gonna say while test arrow node data is less than, nope, let's rearrange that. I want to use a less than. And so it's going to be data to insert is less than test arrow node data. Now that's not enough. Let us think through this a little bit. What if everything in the list is less than the thing that we want to insert? This will walk off the end of the list. You know, I've got the numbers 1, 2, 3, 4, 5 in the list, and I'm trying to insert 10. And I'm going to say, is 10 less than 1? No. Move. Is 10 less than 2? No. Move. Is 10 less than 3? No. Move. Is 10 less than 4? No. Move. Is 10 less than 5? No. Move. And now test becomes null. And if we try to say, is 10 less than test, which is null arrow node data, that's a seg fault. That's an absolute segmentation fault. So it turns out I'm going to have to put in another conditional in here, and that is test does not equal null. Okay, and I put that first because of this short circuiting of and statements. Okay. And oh my God, I just realized I did not share this screen. Sorry about that. You've just been listening to me prattle on now for about 5 minutes, and this is what I've been writing. Okay. So my apologies on that. That was stupid. I'm just going to call it a day at this point. We'll pick up here tomorrow writing the rest of this this pseudocode for insertion into a linked list. Today's not starting well. Hopefully it won't be as bad as yesterday, but boy, you know, this just isn't starting well. I'll post the lecture now. I'll see y'all tomorrow. I keep thinking tomorrow's going to be a better day. Tomorrow's going to be a better day. I will tell you this. I teach data mining, data analysis. I love data. I love looking for patterns in data. And yesterday, you never consider a single data point to be a trend, but we'll see what happens today. But there was in the data, the coronavirus data for Michigan, there was a little bit of a bright spot for Michigan yesterday. And we'll see if that continues today or if that was just simply a blip. So, and so with that, I will let you go for the day. So I'm going to escape out of here, save that.